we want to find an approximate graph of our function knowing that our first derivative and our second derivative look like this. Alright, so to analyze the graphs, I'm going to break it down to separate parts real quick. Let's just look at the first derivative. I'm going to start labeling, I'm going to say this is A right here. Let's call that point right there B, and this point right here C. Okay, so between negative infinity and A, it says my first derivative is negative. Okay, so between negative infinity and A, because my first derivative is negative, that means my function should be decreasing. Okay, now from A all the way over to C, since my first derivative is above the x-axis, so from A all over to C, my original function should be increasing because my derivative is above the x-axis. Now everything past C, so C to positive infinity, again my first derivative is below the x-axis, so my first derivative is negative, so I should be decreasing. Okay, let's do the exact same thing now with our second derivative, which is this line. So from negative infinity up to B, so from negative infinity to B, my second derivative is positive because it's above the x-axis. So my second derivative is positive, so I should be concave up. Okay. After B, so from B forever the rest of the way, so B to positive infinity, I'm below the x-axis with my second derivative, so my original function should be, with having a second derivative is negative, should be concave down. Okay, so when I want to go and draw my graph for my main function, I got to consider all these in mind. So let's put an A right there, let's put a B right there, and let's put a C right there. Okay, so from negative infinity to A, my graph is decreasing, so it's coming down. Let's say I'll just do a point right there. It's coming down to there. And then from A to C, my graph should always be increasing. So it should always be up. But the thing is, from negative infinity to B, somewhere halfway along the way, I change from concave up to concave down. So let's make this our changing point. So all along here, I'm increasing, but I'm concave up. And then after that, I'm concave down. Let's see, after C, I'm start decreasing. So let's say I go up to this point here in C, and then I start decreasing. Alright, so let's see if I actually got this all. It's kind of hard to keep this all straight. You almost get cross-eyed, trust me. Okay, let's double check all this. From negative infinity to A, so from all the way from the left down to A, I should be decreasing. I've got that. From A to C, my graph should always be increasing. I've got that, so I'm always going up here. And then from C to infinity, I should be going down. Okay, got that. From negative infinity, so on the left, all the way up to B, I'm going to be concave up. So concave up all the way up to B. That looks great. And then B beyond, I should be always down. Looks great. So that's just one potential graph right there. That's a little way of how to see it. Okay, example 5. We want to graph this last function here. And what it's just asking us to do is it's a way to wrap up this section and just put all of your knowledge together, roughly. Okay, so if I want to, let's talk about our domain, first of all. Okay, I need to figure out when that denominator is going to be 0. So x squared minus 2 is not allowed to be 0. X squared can't equal 2 square roots, so plus or minus the square root of 2, which basically says then x cannot equal basically 1.4, plus or minus 1.4. So that's where we're going to have asymptotes on our graph. So let me go ahead and why don't we just go ahead and start forming our graph right over here on the right. 1, 2, putting some values on here. Okay, about 1.5, 1.4, we got an asymptote sitting there. Another one sitting right there. Okay, so that's a good start to our graph. Now let's get our intercepts. For our x-intercept, we're going to set y equal to 0. So 0 is equal to x squared minus 4 over x squared minus 2. And again, we're just going to focus on the numerator. So 4 is equal to x squared, or x is equal to plus or minus 2. So we have an x-intercept there, and we have an x-intercept there. For our y-intercept, when you plug in 0 for the x's, you get basically negative 4 over negative 2, which is a positive 2. Okay, so that's going to take care of that. Let me erase all this stuff, and let's come back now and start with our first derivatives and our concavity and everything. With our first derivative, we'll get y prime to equal the bottom times the derivative of the top minus the top times the derivative of the bottom. Whoops. I'm saying it, but I'm not doing it. Bottom times the derivative, bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay, and since we're going to be just more interested in setting this equal to 0 to solve, I'm really going to start ignoring the denominator, because all it does is when we want to set this equal to 0, it just focuses on the numerator, just like it did earlier when we were dealing with the x-intercepts. Okay, so just looking at the top, let's go ahead and multiply this out. So we'll get 2x cubed minus 4x, and then watching our signs closely, minus 2x cubed plus 8x. It looks like the 2x cubes are going to cancel each other off, so we have 0 is equal to 4x, or x is equal to 0. So we have a critical point at x equals 0. Okay, and if we want to go ahead and test it while we have this here, we're going to plug in 0, test to the left and test to the right in our first derivative. So testing to the left, if I plug in just say x equals negative 1 and then x equals 1, what's going to happen, and y'all can just trust me on this or go with it, but negative 1 on the left and positive on the right. So we should be decreasing down to 0 and increasing past 0. And like I said, y'all would be more than welcome to definitely go in there and double check me on that. But so I'm going to be coming down to 0 and going up past 0. So that's basically what our graph looks like. And that's just showing us that definitely for sure we have a critical point. It's actually going to be a minimum value. Okay. So let me erase some of this real quick. And then we're going to come back, and now using this we're going to find our second derivative. So y double prime is going to be the bottom. Why don't we go ahead and actually, let me leave that top cleaned up. Let's make this easier on us. Since it cleaned up so nicely when we actually did find the critical point, let's write it in the cleaned up version. That would be the smart thing, wouldn't it? Okay, so y prime, what did we decide it actually cleaned up to be? It was just 4x on the top and x squared minus 2 squared on the bottom. It's going to be much, much, much easier that way. Okay, so y double prime is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And the derivative of the bottom would be 2 times x squared minus 2 times 2x. Okay, and when we want to set this equal to 0, let's see if we can clean this up though. 4 times x squared minus 2 squared. Let's see, 2 times 2 is 4 times 2 is 16, so minus 16x squared times x squared minus 2, all over that denominator squared. Okay. And when we set this equal to 0, so we can find our points of inflection, we're just going to focus on the top. So 4 times x squared minus 2 squared minus 16x squared times x squared minus 2. Let's move that term over So 16x squared times x squared minus 2 is equal to 4 times x squared minus 2 squared. Okay, they both have this common, x squared minus 2, so we'll cancel the 1 here with one of those there, leaving 1. The 4 goes with that 16, leaving a 4 right there. Okay. So what's left? I'm going to come over here on the right. So over here on the left. So I'm running out of room here, but we have 4x squared is equal to x squared minus 2. So 3x squared is equal to 2. X is equal to 2/3, or x squared is equal to 2/3. So x is equal to plus or minus the square root of 2/3. Okay. And just taking a check real quick, let's look back at our work. Looks like actually, I'm sorry, right there, that should be a negative 2 sitting in there. And so when you get x squared equals 2/3, we get a negative in there, and we can't do that. So what we just found out, there's no points of inflection. Okay. All right. So come back into our graph. We'll just say there's no points of inflection. Okay. So going back into our graph, then what exactly is happening? How are we going to decide what's going on? Well, going down that checklist of all the steps that we had to do in order to graph a function, there's 2 last points on there. One of them was to check for final asymptotes, and then the last one was just to pick some general points and plug them in. Okay. Now we got our vertical asymptotes just by finding our domain, but we also have a horizontal asymptote. Do you remember going back to our function that since the degree in the top is equal to the degree in the denominator, because the degree in the top is 2 and the degree in the denominator is 2, that we actually have a horizontal asymptote, and it's always the coefficient over coefficient, so it's going to be y equals 1 over 1. So y equals 1, we have a horizontal asymptote right there. That's great, because that really helps us out figuring out what to do. Obviously, our graph is going to be, because we have some x-intercepts right there, our graph's coming up, but keeping sandwiched right there between those 2 asymptotes, and the same thing right here on the left. It's coming down, it's being sandwiched in between those 2 asymptotes. Okay, so all of this right here would be an example of the graph for y equals x squared minus 4 over x squared minus 2. And honestly, if I wanted to, I could plug 3 into the equation, 4, -3, -4, get some values, and I bet you'd follow right along that exact same pattern. But it's always nice to have those asymptotes there because they're definitely a guide for the function.